As you can see, I'm still working on this NCR computer, and this repair's taken a bit of an odd turn. Very unusual fault we have here. There's a number of faults on this machine, and the one in particular I'm looking at the moment is trying to get it to read the floppy disk contents and try and boot from the disk. Now, in the previous videos I've gone through showing that the data's being successfully read from the disk, and also that it seemed to be making it through to the actual DRAM, and we'll look at that again in a few minutes when we look at the logic analyzer. So what I've got hooked up now is, as well as the DRAM, the floppy drive controller, I also have all the lines on the Z80 hooked up. And what I've been doing, I won't show you this in the video because it's very time consuming and fairly tedious, is I've been stepping through the code. I found a listing for the ROM, and I've been stepping through the code, seeing how it works and where it could be going wrong. So it's a very basic boot up ROM, doesn't really do very much. The startup, it just initializes a few bytes in RAM. It then goes through some self-tests, tests the RAM and the ROM and that sort of thing. Very basic test, doesn't test them in too much depth. And if the drive door is open, then it then goes into a tight loop waiting for a key to be pressed on the keyboard. If the key you press is not the carriage return key, it ignores it and carries on waiting. If it is the carriage return key, it vectors off and tries to recalibrate the floppy drive, but then for some reason it jumps back to the start of the waiting loop and it seems to hang. If the drive door's closed, it does seem to successfully read the disk, in that it will present all the correct or apparently correct bytes to the DRAM, and all the signals look perfectly okay. We'll have a look at those in a few minutes when we look at the logic analyzer. Once it's loaded the initial bootloader, it tries to load the startup code into RAM, and the essentially the bootloader, the second stage bootloader, is loaded into DRAM starting at address 2000 hex. Once it's loaded that, it tries to hand control to it starting at 2000 hex. But one of the first things it does after it thinks it's loaded the code from floppy disk is it examines a few of the bytes that it's loaded to see if they are what it expects, and if they're not, it rejects the disk as being non-bootable. And that's what it's doing. It's we've got what should be a bootable disk here, and it looks at 7 bytes towards the beginning of the code, and again we'll look at these in a few minutes. The first one it looks at is always correct, but the second one is always wrong. And because the second one is wrong, it assumes that the text is wrong that it's looking for, and it aborts the operation and puts a message on the screen saying that it's not a boot disk. But having looked at the code in the ROM and the code on the floppy disk, they match, they are the same. So quite why it's rejecting it is a bit odd, and you'll see that as we go through this video. So what I've been doing is comparing the code, the data seen by the Z80, and comparing that to the code, the data coming out of the DRAM and also going into the DRAM. And they actually match, they are the same, but the data coming out of the DRAM is incorrect for all but the first byte. It's not the first byte it loads, it's actually the 4th byte in the data it loads from the floppy disk. Now, just to try and eliminate the possibility that it just wasn't then stepping on and correctly reading the next byte in RAM, you can see I've changed the ROM in this. I've modified the ROM slightly. I tried a number of things. The first thing I did was to try and eliminate the possibility of it maybe just being a faulty DRAM, because the 4 of these are still soldered in, and I didn't want to take them out if there was no reason. So I modified the ROM so that it was trying to load the code into RAM address starting at 3000 hex rather than 2000. And it does exactly the same thing, and it even returns the same value. It is of course possible that the DRAM is faulty in a way that the entire block is returning the wrong value. but it does pass the RAM self-test. Very basic self-test, but it should pick up that particular issue, and it doesn't flag anything as being wrong with the DRAM when it does the self-test. So I tried that, it didn't make any difference. I then tried changing it so that it was looking at the second byte, just to make sure it wasn't just sticking and unable to step from the first byte in RAM, that it's checking to the next byte. But when I did that, it still returns the same value. So we'll have a look in this video. I'll show you what I've found so far, and then just explain what the next steps in this repair will be. So we'll move the camera. So what we've got here is we've got data coming from the Z80 itself and data coming from the DRAM. In between, of course, we've got the DRAM controller and the DMA controller and a lot of glue logic, but that doesn't really matter as long as all the signals we're seeing at the DRAM and the Z80 are correct. What's in between, in theory, shouldn't matter, and must be working if those signals are right. So I'll move the camera and we'll have a look at what we're actually getting back from this system. So what we've got on the analyzer, of course, is the address. The one at the top is the address directly on the Z80 itself. We've got the DRAM address. Now this is inverted in the analyzer because, as I said in the previous video, it comes out of the DRAM controller inverted. Shouldn't matter as far as the DRAM itself is concerned, but just bear that in mind. What we're seeing here is not what you would see if you probed the pins directly, but it is coming directly from the pins on the DRAMs. We've then got data. The first data is the data as seen at the Z80, and the next one, the DRAM D, is the data seen directly on the pins of the DRAM. RAS, CAS are the RAS and CAS pins directly on the DRAM. The right, just the W, is the right line going into the DRAMs, and the DRQ is the DRQ line coming out of the floppy drive controller. So using this method we can step through to any part of the code we want. All we need to do is put in the address that we want to try and trap. I won't show you the source code, at least not all of it anyway. And then you can just work your way through it based on what you see. I also tend to set the M1 line when I'm trying to capture data on the analyzer, so I'll set that to active low, and the reason I do that, we'll actually do this in a few minutes, the reason I do that is because as I said, the system does self-test the ROM and the RAM, so we hit each of the addresses several times before we get to the part we're actually looking for, which is the instruction fetch. And of course, by looking at or including the M1 as part of our criteria for starting the analyzer, then we can be sure we're actually capturing the fetch of the instruction, which is what we're interested in, rather than just access to a particular address. Okay, so what I'm going to do, just to save a bit of time, is I'm going to put the disk in and close the drive door, and we'll set the analyzer to trigger when the DRQ line goes high, and this will allow us to see the data that's being read from the floppy disk. So I'll power up the machine, but I haven't armed the analyzer just yet. We'll wait until the machine finishes booting. Just bear in mind this is a replacement ROM, so some of the self-tests are not being carried out, but it doesn't actually affect this particular test. In fact, what I'll do to avoid any confusion, if you are looking at the source code, I'll just put the original ROM back in so that that's exactly the same as the code in any document you might be looking at. Okay, so that's the original ROM refitted. We'll boot the machine back up. Okay, so we've got the message on the screen of the NCR saying that we should mount the operating system disk, which is the one that's already in there. If we don't put a disk in at all, we get a drive not ready message. So it is seeing the disk and reading it. But what we can do now is, on the analyzer, I'll press the return key on the keyboard, and as you can see, we've captured some data. And what we can do now is scroll through this, and we're at the point in the code where it's loading the data from the floppy drive, and then copying it to the DRAM. Goes through the DMA and the DRAM controller, but as you can see, the data we are seeing, so we've got the address at the top, that's the red one is the Z80 address bus. The DRAM address comes in two chunks, low byte first, so 00, and if you follow this down, the green trace here is the RAS signal, so where that goes, where it drops, that's the data, or the address rather, that's latched into the DRAM. The address then changes, and where the CAS line goes down, that's the blue one, that's the upper byte of the address that's latched into the DRAM. You can see they're both correct. I've got this in state mode, so the timing of these is not quite right. I have tried this in timing mode with the capture set at 2.5 nanoseconds, and we can then see that these are properly sequenced, and the falling edge of the right is slightly after the RAS, which it should be. So these are correct, and the data value we're seeing is indeed C3, and that's what it should be. If you recall the code we looked at in the previous video, so I'll just refresh your memory if you've forgotten this. It's C321, and then it says 00 here, but we'll see 20 because that's the offset to the start of where this is being loaded. So C3 is correct, and then if we scroll across another 32 microseconds, we'll see the next byte. So you can see that the data that's being presented to the DRAM is correct. Now that first one reads back correctly when the system tries to branch to it. The next one you can see is 21. This is not the data that the system's trying to check. It starts at the fourth byte. But you can see that each of these is correct, and these signals, the RAS, the CAS, the write, are correct. And there aren't any other signals going to the DRAM apart from the address and the data, and they're all correct. So what I'll do now is I'll scroll across to the point where we see the first byte that the system is trying to check. Okay, so this is the position. We're kind of 131 microseconds in now, and this is the byte that should be written to address 2004, and again the correct address is being latched in, both the lower byte and the upper byte, and the right line is correct. Again, this right line is the line that's directly connected to the DRAM, and the address matches what's on the Z80. Now it doesn't necessarily have to match, of course, because the address that we're seeing at the DRAM is coming through the DMA controller. So the other thing is the data is also correct. So you can see that the data is properly propagating through the machine, and it's the right value. So this is where the system starts going wrong, that this value, when we come back to read it, will read as 10 hex, not 50. If we go on to the next byte, you can see this is the correct value as well at 4D. If you go back and look at this, I don't know if you can actually see this, but the three values the system is checking is 43, 50, 4D. Actually check 7 bytes. This is actually wrong. There are some bytes missing off here. It's actually this text, and that is actually in the ROM. It's just this has been written out wrongly. So I'll quickly go back to the first byte, which is at 2003, just to prove that's 43. But as you can see, all the bytes seem to be correct. Okay, so at address 2003, the address coming in to the DRAM, both chunks is correct. RAS and CAS is fine. The right line is exactly as it should be, and the data is showing at 43, which is exactly what it should be as well. So all these are correct. It's very odd that, incidentally, the reason there's a delay between the data that the Z80 is seeing and the data that the DRAM is seeing is because the data to the DRAM comes through the DRAM controller, whereas the data bus that the Z80 is seeing is directly on the data bus itself. Okay, so these are all correct, so we should be seeing the correct values in RAM. However, what I'll do now is change the triggering of the analyzer. So we'll get rid of this, we don't care about this anymore. And I'm going to put in a value here. This is the part of the code. Now you won't want to see this, but if you scroll through the code far enough, you'll find this section. And this is part of the system loader. And what it does, once it's tried to load all the data into RAM, it comes down to this point, and it tries to check the 7 bytes that we just looked at. And the 7 bytes in RAM are further on in the RAM. It supports 3 different versions, and the one we're interested in here is the top one. I don't know if you can see it, but the values we're looking for, the data values we're looking for, 43, 50, 4D, 20, 32, 2E and 32. And if you recall from the data we just looked at in the listing for the disk, that's an exact match. These are the 7 bytes it's looking for, and these are the 7 bytes that we've just seen it writing to DRAM. So all the code does that's checking this is it loads a pointer to 2000 hex, and it's actually loads a pointer to 2003 hex, because that's the first byte it's looking at. It's looking at the 4th byte it tried to load into DRAM. It loads B with 7 because there are 7 bytes it wants to look at, and then it goes through checking that those 7 bytes match what's in the little table in the ROM itself. When we go through this, you'll see that the first value is correct. It will see that, it will be a match, it will move on to the second value, but then it will reject it because the value that's returned from the DRAM is incorrect. So we'll try capturing that on the analyzer. So the address of that block of code is 73D, so I'll put that in, 73D. Now, as I said, it will hit that address several times when it's doing RAM tests and the checksum tests for the ROM. So just to make sure we capture the actual instruction fetch, we'll also set the trigger so that it triggers when M1 is low. So these 2 conditions have to be met for it to trigger. If we now arm the analyzer, and I'll press the return key, we've captured some data, and we'll now scroll through seeing what's going on. So this is the beginning of that block, and the first few instructions are just the first instructions where it's loading the 2 registers with the value that he wants to use. The value in the red trace at the top is the address on the Z80 bus. So this is the address it's putting out when it's trying to fetch the instructions. So we'll scroll across, and when we get across to here, the address 793, let's bring back this listing. Address 793 is the first byte in this table, so it's value of 43, that's in the ROM. So if we go across, you can see that value is in fact correct. It's reading the value from the ROM, 43 is what we expect, and it's now going to compare that by reading the value at address 2003 in the DRAM. So if we scroll across, you'll see address 2003 pop up, and you'll also see, if you look at the various lines, the RAS and the CAS, that the address is correct as well. So the low byte of that address, 3, is latched in when the RAS line drops, that's correct, and 2000 or 20 for the upper byte is latched in when CAS drops. The right line is high as it should be because we're reading, and what it reads back. So the value shown in the green trace is the data value as seen by the Z80, and the value in the turquoise trace is the data value coming out of the DRAM, and they're both a match. So the data's coming from the DRAM, that's been read correctly, that's what we wrote into it, and it's propagating through the board and successfully getting to the pins on the Z80. If we keep scrolling across, it will now loop round and check the next byte. So if we keep going round, you'll see that eventually we'll get to this part, so address 794. That's the second that's the address of the second byte in the ROM that we're trying to check, and it should have a value of 50. but the value we're reading from the ROM at that address is correct. It's 50, and that's what it should be. If we keep going across, we'll come to the part where it's going to compare that. So it's from address 2004. The DRAM is being correctly accessed, so the lower byte is 4, which it should be, and that's what's latched into the DRAM when the RAS line drops. And same with CAS. These appear to be out of sequence, but it's just because I'm in state mode. If we actually capture this using timing mode, there is a 50 nanosecond offset on these, which is correct, so don't be alarmed that these are showing at the same time. It's just the way the data is being captured on the analyzer. In fact, I'll change this to timing mode in a few minutes and we'll rerun this test. But I'll do it in state mode to start with, just because it's clearer. When you put it into timing mode, you'll get repetitions of clock cycles for a given data value. Okay, but the correct value for the lower byte and upper byte are as they should be. It's still in read mode, but the value that's coming back is actually 10, not the value of 50 that it should be. If we go on, and at that point it then jumps back, so this returns now the function. If I can find it, the function, it checks each byte as it's going through this, and if any of them don't match, it just returns, and that's used as a flag to the system that the disk is the wrong disk, and then it puts the message on the screen saying effectively that's not a boot disk, when clearly it is. So what I'll do now is I'll change this to timing mode so that you can see that the relative timing is not the issue on this. So into timing mode, and it's set to 10 nanoseconds. That's easily enough resolution for what we're doing here. We'll arm the analyzer and then hit the key. So we capture, you'll see why it's less clear with timing mode. We capture multiple events. But the point here is just look at the lines we're interested in. The address, data, RAS, CAS, and the right line is what we're actually interested in here. So I just need to change the trigger. Fortunately, this analyzer changes it saves the trigger mode with the state. So we'll need to change this again. So I'll just put back in what we had before. So we want 7.3D, and we want M1 low. So we capture the instruction fetch. Arm the analyzer, press the key again. Okay, and what we should now have is the same bit of code we were just looking at, but the timing for or the relative timing of the signal should be clearer. So you can see that as we go through, we'll get to the point where it's reading the value that we're interested in. So 793, that's the value in the ROM. It reads that, it's a value of 43. And if we then go on to where it's comparing this from 2003, which is in RAM, then notice that the address is correct, but now the relative timing of the RAS and the CAS signals is also correct. If we go on to the next byte, which is what appeared to be a bit odd before, so 794 is the value that's been fetched from ROM 50, and if we keep going to where it's comparing that, so 2004, notice now that the relative timing of the RAS and the CAS is correct. It was just apparently synchronized before at the same time because we were in state mode. That's one thing to bear in mind if you use state mode. If you're looking at relative timing of signals, then it might appear to be incorrect. But as we can see, the system's doing exactly what it should do. We've got the low byte of the address, the high byte, they're latched in correctly. We're in read mode, not write mode, and that's really all. The signals going to the DRAM, there aren't any more, and the data coming out of it, which is this is directly connected, the turquoise is directly connected to the DRAM, is coming out as 10. and it comes out as 10 whatever address I set, or whatever address range I set. So if I change the address range in the ROM to 3000 or 5000 hex, it still comes out as 10, and that data is the same value that's also getting through to the Z80, which is why it fails, because obviously it doesn't match 50. And then if we keep going, you'll see it return. So this EFFE followed by the EFFF is of course the top of stack, because we're just returning from a function call, and the return address is where it was called from in the first place. So as you can see, there's something very strange going on. I'll just move the camera back down. Okay, so that's the testing I've done. I've done a lot more testing than I've covered here. I've gone through quite a bit of the code using this same technique, and what you can do is, if you want to look at a bit of code, to set that as the address you want to trap, set the M1 as part of the criteria for capturing, and then you can effectively step through. You can't, of course, single step the machine, but you can effectively see what it's doing one clock cycle at a time. So this is why my suspicion's now falling on the DRAM itself. If it is a DRAM failure, it's a fairly odd mode of failure for the DRAM, especially considering that the self-test passes. But that's what I'm going to do next. I'm going to remove the remaining 4 DRAM that are still soldered to the board. I'll fit sockets, and then I'll try a complete new set of DRAM to see if that makes any difference.